Good afternoon, everybody. Let's start our lecture today. Now, in our previous discussion, we have introduced up to you how to solve a simple differential equation, and we have be able to apply those methods to the problem of projectile motion in a viscous medium. We respectively solve the projectile motion without gravity. And so they can be combined. The solution can be combined to solve the projectile problem in the viscous medium. Now, but we also have discussed about using other methods to solve those differential equations. And especially, we introduced to you the method of using integration to solve that simple differential equation. Instead of guessing the solution, the equation of motion can be integrated, okay, by rearranging the differential. We can put all the, for this simple differential equation, we can put all the all the velocity on one side, and all the time dependent on the other side, so that the two sides can be integrated together to get the solution. And that's what we've done. We have done in the previous lecture. We just integrate both sides, and you can do it either by indefinite integral or by a definite integral. In both cases, you arrive at the solution that we have found previously in our first encounter of this differential equation. Now, the method is a bit more general than the guessing solution method, because sometimes you may not be able to guess a trial form of the solution correctly, and in those cases, it is recommended you can solve the differential equation by using a direct integration. Now, suppose the drag force, the air resistance, is now given not proportional to the velocity itself, but proportional to the square of the velocity. So the drag force can be written as minus beta v square, where beta is a positive constant. In that case, you may not be able to guess the solution, the trial solution. So it may be better if you can solve this equation by using the direct integration. Now, so can you write down the equation of motion? You are given the force now, and so the force is equal to ma, right, by Newton's second law. So you can write down the differential equation in terms of v, right? And so how would you solve it if you are required to do integration? Anybody have done it at home? Have anybody found the answers to this problem? If not, I just give you several minutes to do it now. So maybe 5 minutes. I think you should be able to at least to integrate it. Maybe just pick out a piece of paper and try to work on it. Now the differential equation looks like this, right? By Newton's second law, we have m dv dt be equal to beta v square, right? And so when you divide by m, and I define the constant b as beta of m, then I arrive at this differential equation. Is that right? So how do you integrate it? The idea is similar to what we have done before. We just put all the v's on the left-hand side and all the t on the right-hand side. Okay, and we do the integration on both sides. You try to see what you got. Okay, you try it now. So anybody has got the answer? What's the answer to this problem? Can you show me the answer, your answer? Let's do it together. Let's do it together. We integrate, right? We integrate this one with respect to dv. And on the right-hand side, we simply integrate dt. And so the rules of integration tells us that this is v minus 2 plus 1 divided by minus 2 plus 1. This is the power. This is the power alpha. So you integrate v to the power alpha, then you have v power to the power alpha plus 1 divided by alpha plus 1. And on the right-hand side, you then have bt, but you have the integration constant. Is that right? So what would be the case? You now have 1 over v, which is negative because of minus 2 plus 1, be equal to minus bt plus c. So what is the initial condition? The initial condition is that when at time t equal to 0, the object at t equal to 0, the initial velocity is v naught. This is the velocity with which the object is projected into the medium, right? And so, and that means if you put t equal to 0 here, then v should be equal to v naught. And that means c is equal to 1 minus 1 over v naught. Is that right? And so you can write out the full solution now. The full solution is something like this. Is that right? Now we want to cancel all the minus sign, and then we take the reciprocal to get v as a function of the time t, right? And so this is just what? This is just v naught divided by 1 plus v naught bt. Is that right? So this is a solution. Now you see this solution makes sense because initially you have velocity v naught, right? When t is 0, obviously you have the initial velocity v naught, and at times go, the t is getting bigger, and so v naught is divided by a number that is larger than 1, and so the velocity will decrease. Now, how would you define the time scale here? If you are required to define the time scale for that characterize how fast the velocity change for this problem, then how would you define time scale? Anybody knows the answer? Now I would define it like this. Because I know in the denominator, 1 is added to v naught bt, right? So that means v naught bt is dimensionless. Otherwise, it cannot be added to 1, right? And if this combination is dimensionless, it means the product v naught b must have the inverse dimension of time. Is that right? Otherwise, it cannot be multiplied by t and becomes dimensionless. And so we can define the time constant like this, the time scale tau like this. I can define it as v naught b, 1 over v naught b. Okay, so with this time scale, I can rewrite the velocity as, this is a definition. So I can rewrite the velocity as t over tau. So at t equal to tau, when the time t is equal to tau, the velocity obviously decay to half of its initial value. So this is the time scale that characterizes how fast the system change. Now, the interesting features is here. You can see that in our previous example of when the resistive force and the viscous force is directly proportional to v. In that case, the time constant, the time scale tau is simply 1 over b. without the V naught, right? Now with the resistive force proportional to V squared, but not V, the time scale tau now has the constant V naught. It is inversely proportional to V naught B. It is the reciprocal of V naught B, which contains the initial velocity V naught. So in this situation, the initial velocity doesn't matter. It means that if you are projected with a higher initial velocity, then the system simply decays faster. In the first case, when the viscous force is proportional only to V, the initial velocity does not affect the time scale. The time scale is affected solely by the constant B. Okay, but now if the resistive force is proportional to V squared, we can see that the time scale depends all on B, but also on V naught. If the V naught is large, if we project it into with a high velocity into the medium, then the resistive force is very large and the velocity will decay quickly. That is what this equation means. Okay, so when you do a calculation, after you do a calculation, be sure you know the physical meaning. You can see from this equation that there's why the tau depends on this combination, and how this V naught, how the B affect the timescale tau, and what is the meaning behind. So I share this with you. So let's go back to our discussion, to this slide. Now, how about the second order differential equation? In our discussion for the simple harmonic oscillation, right? We come up with the second order differential equation, but not the first order. But now it is expressed not in terms of the velocity, but in terms of the position. Okay, this is actually defined as the equation for simple harmonic oscillation. Okay, now but what then? In this case, there's no way for us to integrate it. Okay, we cannot do the direct integration like this because x is not a known function of t, and so you don't know how to integrate it to get the x dt, right? So that is not possible. And in the second way, we tried in a previous discussion, we try to rearrange the equation such that all the v is on one side, the other all the t is on the other side. But this is not going to work because it's a second order differential equation, but not the first order. So you are not able to rearrange the differential. Now I will let you see what it looks like. Now, what we call the square x dt square is the second derivative of x with respect to with t, and it is in fact like this: d dt of dx dt, right? It's something like this. The second derivative of x. I write bracket. Now, this is the velocity, so it is dv dt, right? Now, if the right hand side, if this variable is x, then we can rearrange the equation, rearrange the differential such that the left-hand side consists solely of terms that involve v, and the right-hand side is solely in terms of t. But now we cannot do that. Why? Because you can see this is not v, this is x. Even if you put the x to the left-hand side, the left-hand side becomes dv over x. But both are unknown function, right? X and v are not the same, and both of them are unknown function to you. And so you are not able to integrate it in this way. Now, there's a special way for you to integrate this equation. I will talk to you more about it when we discuss about the energy. When we talk about work and energy, we'll discuss how to integrate this equation. We actually have some methods to integrate it, but it's not that direct. Okay, so we do not proceed further here until we discuss about the problem of work and energy. Now, how about if we cannot integrate the equation? there is no guarantee for you to solve that differential equation. If the differential equation is very complicated, if the motion is very complicated, you simply cannot solve the differential equation in a closed form. There's no definite way. There's no way for you to guarantee that you can do the integration, right? Integration is not as straightforward as differentiation. You may not be able to express an integral of a function in a closed form in terms of the elementary function. So if you cannot do that, then what should you do? One of the methods is to rely on numerical solution. If you want the solution to be a number, if you want the curve to be calculated, expressed in terms of numbers, then numerical solution is the best method. And it is actually used in modern scientific research. In modern scientific research, we come up with very complicated differential equations that are only solvable with numerical solution. But that doesn't matter because we have a very strong computing power. Nowadays, we have very good computer, and solving this kind of differential equation is no difficult for the computers. So we are going to let you see how to do it. Now we go back to the kinematics equation that we learned before. The velocity is given as a time derivative for the displacement, right? And the acceleration is a time derivative of the velocity. These two expressions are exact. They are the instantaneous velocity and instantaneous acceleration. And they are given in terms of the time derivative, right? Now, but we emphasize that in our course of discussion, we emphasize that if we consider a time interval that is sufficiently small, then I can replace the derivative dx dt by a finite ratio of two finite increment, and that is delta x over delta t. We can replace dx dt by delta x over delta t, and we can also replace dv dt by delta v over delta t. Now this approximation is good, provided that delta t is sufficiently small. Now, how small is sufficiently small? We will come to this problem later. It turns out that if the delta t is much smaller than the typical time scale of variation of the problem, then we regard delta t to be sufficiently small. Okay, and in this limit, when delta t is sufficiently small, these are good approximation. Now you notice that I don't write the exact equal sign here, but I write a tilde equal sign, meaning that the equality is not exact, but it's approximately correct. And the reason why these two expressions are only approximate is that because V and A are both not constant in that time interval. They are changing slightly. Even though the change may be small in the time delta t where delta t is sufficiently small, they are still changing. And so that's why they are not exact. You only have, for delta x over delta t, you only get the average velocity, and delta v over delta t, you only get the average acceleration in that time interval. And although when delta t is sufficiently small, the average quantity is very close to the instantaneous quantity. Okay, now so we proceed with this equation, okay, and see what we can do for a long time interval. For a long time interval, we can always divide that time interval into many small steps. And we label the step as 1, 2, 3, 4, 5, 6 up to n. We divide it into n small steps. And each step has a small length of delta t. And so we label the time of the time step as t1, t2, t3 up to tn. Now delta t is the length of each time interval. And the t1, t2, t3 are the time at the time interval 1, 2, 3, 4 we define. Now, so in solving the motion, we are given the initial velocity, right? And we are given the initial position of the object, and we are required to predict the subsequent motion, the subsequent position, and subsequent velocity of the object. And so we are given the first step, right? And we are going to calculate the x and the v for the latter step. Okay, so how do we do it? We are given x1, we are given v1, that is the initial velocity and the initial position, right? But we know that the velocity in the first time interval is equal to approximately equal to delta x over delta t. But what is delta x? Delta x is x2 minus x1. x2 is the position of the object at end of the time interval, while x1 is the position at the beginning of the time interval. So x2 minus x1 gives you the delta x divided by the time interval delta t. And similarly, the acceleration in the first time interval is approximately equal to the final velocity at the time interval v2 minus the initial velocity v1, okay, divided by delta t. Is that okay? We simply apply this two formula in the first time interval. That is the time when we go from t1 to t2. The velocity at t1 is v1, the position is x1, and at time t2, the position x2 and the velocity is v2. We are discussing about the first time interval. Now, but we can make it more general. Suppose we go from the step ti to I plus 1. So the time is from ti to ti plus 1, where I is a general number, is a general integer. So we can write the same formula, right? The velocity in the ith interval is approximately equal to the position xi plus 1 at the end of that time interval minus the position xi at the beginning of that interval divided by delta t. And similarly, the acceleration is the velocity at the end of time interval vi plus 1 minus the initial velocity vi divided by delta t. Is that right? So this is the general formula. If I put I equal to 1 here in this form, in this two formula, I go back to this, right? Okay. Now we arrange the two formula such that we make xi plus 1 and vi plus 1 as the subject of the formula. Okay, so I solve for xi plus 1. Xi plus 1 is then equal to xi plus vi multiplied by delta t. And vi plus 1 is equal to vi plus ai multiplied by delta t. Is that right? Now we succeeded in making the quantity at the end of the time interval as a subject of the formula. They are expressed in terms of the quantity at the beginning of the time interval. So we proceed a small step forward by lowering the position and the velocity of the object at the beginning of the time interval. We can proceed a small step forward to calculate the position and velocity at the end of the time interval. So we proceed a little bit forward. Okay. Now, so we can proceed step by step forward so that we can solve the whole motion. Now, in doing this calculation, we are given the acceleration function. We know that x as a as a function of x and v. Okay, we know that this function. This is given by the force law. If it's a spring or is subject to air resistance, then we have a known function of the force in terms of the position and the velocity. And so divided by m, we find the acceleration. So we know this function. And we are given the initial position of the object and the initial velocity. So with the initial position and the initial velocity, we can substitute x1 and v1 into this function and get the acceleration at the beginning, which is a1. Okay, so a1 is just defined as a evaluate x1 and v1. Now, so with a1, x1, and v1, we can work on this formula, right? We can put I equal to 1 here, and we substitute a1, x1, v1 into this formula, and we get x2 and v2. Now we can proceed further. After knowing x2 and v2, we can substitute x2 and v2 into the function a and get the acceleration in the second interval, which is called a2. And with x2, v2, and a2, we substitute into this scheme again, and we get x3 and v3. And so the process can be repeated, okay, to x4, x5, x6. Eventually, we solve the whole problem. We find all the velocity and all the position of the object in the different step during that time interval, during the long time interval. Okay. And of course, you probably don't want to do it by hand because you chop the long time period into many small steps. And for each step, you only proceed a little bit forward. So you probably don't want to do it by hand because you have to do it many times. So the best way to do it is with a computer. The computer knows how to repeat things without thinking, and it can do it very efficiently. And so you solve the whole motion in the blink of an eye. Okay. Now let's see how to do it. This is a spreadsheet, Excel spreadsheet. You are now required to solve the free fall motion under gravity. Okay. Now, but you say, well, this problem, I know the solution. Why do you ask me to solve it by numerical method? Now, the idea is to let you know how to do it, so that you can apply this method to solve more complicated problems. So we better start with a problem that we know the solution very well, and that's the free fall motion under gravity. And given G is 9.81 meter per second square, and we make the time step to be very small. How small is that? We make it delta t equal to 0.01. Okay, 0.01 is obviously a small time. And we start from zero velocity. We drop the object from rest, and the initial position is called x1 is equal to 0. Now we first create columns of time, columns of position, columns of velocity, and column of acceleration. Okay, these are the initial steps. Now we then create the columns of time. How do we do that? We want each time interval to be of the same length, and the length is given by the cell B3, right? This cell is given by the value here, 0.01 in this case. So how do we construct that? Now the initial time is of course 0. The first time, the T2, now this is T1. How do we calculate T2? T2 is just T1 plus delta T, right? The two time interval, the two time is just separated by delta T. So I refer to the last cell. Okay, this cell is A7 and the previous cell is A6. So I write E cosine A6. I refer to the previous cell. And I added the small time step delta T. And for delta T, I refer to this cell, which is B3. But I write a absolute address for the time step. Why? Because when I copy and paste downward, I want to keep that time step constant. I don't want that time step to change, right? While when I copy and paste downward, I want the A6 to change because I always refer to the previous time, right? So it would be nice if you can automatically change, but the B3, the time interval will remain constant. So in this case, when I write this, I press the enter, I got 0.02. And when I copy and paste downwards, and I copy a whole column, I got all the numbers. Okay. Now, I write the initial position and initial velocity here. But this is of course the initial position, right? And this is also the initial velocity because we refers to the time 0. So I just copy this from this cell. So I write $E$2 for the initial velocity, for the initial position, and I write $E$3 for the initial velocity. Okay. Now, why do I write this? Because I want to make the things that I want to change separate from this worksheet. This worksheet is for calculation. So I would like to make my initial data and my parameters. I would like to store it in another position. So whenever I want to change it, I can look for it on the upper side of the spreadsheet. Okay. So what is the acceleration? in this case, the acceleration is a constant. So I always refer to this value. So I simply type B2 $B $2. When I copy and paste, it always refers to this cell B2, and with this value 9.81. So I now complete the first row. Okay, and the second row is crucial. How do I find the position and the velocity at the ladder time? The idea is to use this formula. X2 is equal to X1 plus V1 delta T. So I write a dollar sign, equal sign here first, and I refer to the previous position. This is X2. I want to calculate X2, so I refer to X1. X1 is the position in the previous time interval. So I refer to X1, which in this case is a cell B6, this cell, right? Plus what? V1. V1 is the velocity at the previous time interval. So, so this is the velocity at time 0. Okay, so I refer to this cell. So I write C6 multiplied by delta T. Delta T, I always refer to this cell, which is B3, but I write a dollar sign because I don't want it to change upon the copy and paste. Okay, and similarly, I can use this formula to have me find the V2. V2 is equal to V1. V1 is the previous cell. So I refer it to C6. And I need the acceleration A1 in the previous time step. So the acceleration is referred to here. Okay, I refer to this acceleration, the acceleration in the previous time step. So this is D6. And the time interval delta T is just $B $3. Okay, so I press enter and everything is done. And of course, for this case, the acceleration is constant, so I just copy from the previous cell. That is okay. Or I refer to this cell. Okay. Now, so everything is ready. When I copy this row and I paste downwards, I will find that the calculation is automatically done. Because for each time step, I can the variable will automatically change such that it will refer to the previous time step. So every step when I do the calculation, I proceed a little bit forward. And then the accumulation effect of the end rows is that I proceed forward with time in the calculation. And so the calculation is done. Okay. So it's easy. You can easily solve this problem. Now, the good thing about Excel is that when you change the initial condition, the result will change automatically. Suppose I now want to change the initial velocity. I want to project the ball downwards initially, but not releasing it at rest. So now instead of writing it as a 0, I use 1. I project the ball downwards with the initial velocity 1 meter per second. Okay, so I changed it to 1. And after I press enter, this velocity change, and also this column will change automatically. The computer will redo all the calculation for you. So you can change all this value anytime you like. Okay, that is why I write it on the top. It's for your convenience. You can change it anything, any time you like. Even though if I want to calculate the motion not on the surface of the Earth, but I want to calculate the motion on the surface of the moon, I can change this value of acceleration. And when I press enter, when you divide it by 6 for the acceleration on the surface of the moon, you press enter, then you got the whole motion, you got the whole calculation done. Okay. So that is the advantage of using a spreadsheet in a calculation. Now, how about if I want to solve another problem? Instead of solving the known motion of free falling under gravity, I want to solve another problem. For example, the problem about the viscous force that we encounter at the beginning of this lecture. So the acceleration is given by minus bv, right? And I choose b equal to 0.1. So instead of storing the acceleration due to gravity here, I store another constant. That constant is b. And here I choose the b to be 0.1. Okay. Delta t, I choose the same step, okay? And this is the initial position, and the initial velocity I choose to be 1 meter per second. So how do I do the calculation? Now you can notice that I do not need to change the calculation for x and v because they are the general equation, right? These two equations are general. It is true for whatever kind of acceleration you have. So you don't need to change it, okay? Even if you are calculating a rocket flying into the deep space or a projection of a tennis ball, it doesn't matter because these two equations are the kinematic equation and it's independent of whatever acceleration you have, right? So you don't need to change it. The only thing that you need to change it is how you calculate the acceleration. That is the thing you want to change. In the previous example, we enter the acceleration due to gravity in this cell, and we refer to the rate of g that is stored here. But now we are handling a different problem, the problem with a viscous force. So in that case, the acceleration is no longer given by a constant, no longer given by 9.81, but given by this formula. How do I refer to this formula? Well, it's easy. I refer to this formula by typing equal sign, meaning that I want to do a calculation. The b, the minus b is a constant, so I always refer to this cell, $b, $2. And v is the velocity at this time interval, okay? The acceleration is proportional to the velocity and is in opposite direction to the velocity in this time interval. So I refer to the velocity in this time interval, which is what? Which is C6, okay? So I write C6 here, which is referred by this, which is this cell, the value stored in this cell, okay? So I press enter and I copy the whole thing downwards and I just finish the calculation. Now, if you want to solve another problem, you only need to change the equation of motion. You only need to change the acceleration, the function acceleration. And x and v, they are the same. Okay, you don't need to change it. So that means you can solve whatever problem you like. Even though if it's very complicated, you know acceleration as a function of x and v, and you are able to express it here, you copy and paste down, you solve that problem. So in effect, you are solving all of mechanics problem suddenly. You know how to solve all mechanics problem, okay? So that is why numerical method is so powerful. Although it's not beautiful, if you will judge it by the sense of beauty, it may not be beautiful enough, but it's very practical. You have a single spreadsheet, and by entering different function of the acceleration, you can handle different problem. And in fact, you solve all the mechanics problem in one dimension. Now, how about if you are solving a projectile motion? A projectile motion is a two-dimensional problem, right? So that is a combination of two one-dimensional problem. Is that right? We always think like that. Before going to two-dimension, we first solve the one-dimensional case. And by combining that two one-dimensional problem in the two different directions, we solve a two-dimensional problem. And so the spreadsheet, we double it, okay? The time column is still there, but we now separate the x component quantity with the y component quantity. This is the x component, x position, the velocity in the x direction, the acceleration in the x direction. Okay. The acceleration in the x direction is 0 because we are talking about projectile motion, right? So there's no direction, no acceleration along the x direction, and the velocity is here. I refer it to ux. Okay, I refer this to this. So this two equation, it doesn't change, the same before. I do the calculation. And for the y direction, the vy I refer to this cell, okay? And the acceleration in the y direction, I refer to this g, okay? And the calculation is the same before, and we just copy and paste downwards, and we got a solution. Now, how about if you want to plot a graph? Now, this solution gives you at different time t, you know the position x and y of the object, and also you know the velocity vx and vy of the object, right? Now, how about if you are not interested in the time t, you simply want the trajectory. You want to know the path that the projectile motion follow in space. Then how to do? How do you find that draw that projectile? You simply plot. Now we have a column of y, right? And we have a column of x. So if you plot, using x, if you plot y against x, you get the trajectory. You get the shape of the trajectory as it should be a parabola. Okay, so you can extract information from this data sheet very efficiently. Okay, if you like, you can plot a graph of x against t, or y against t, vx against t, vy against t, or you can plot the trajectory y against x. Okay, you can obtain this information very efficiently, and that's why that is the advantage of doing numerical calculation. And in your project, in your solve project, you are required to solve more difficult problem, not that simple problem that you know the answer. You are required to solve a problem with a difficult air resistance that is proportional not to the velocity, but to the velocity square. You are required to solve a pendulum with a large amplitude. You are required to calculate the motion of the planets, which is in general elliptical orbit, but not a circular orbit. You are required to solve the equation that describes the expansion of the universe. All this problem you can do with a spreadsheet. Okay, so that is a beautiful thing. Now we also want to talk a little bit about numerical error. Before letting you have a break, let's talk about numerical error. Now we emphasize that these two equations are approximates, and it approximates exact solution well if the delta t is small. Now, how about if I deliberately make delta t to be very small? Maybe 0.01 is not small enough, so we want better accuracy, so we make it 0.0001. So will it be better? Now, there is a trade-off in doing numerical calculation. Although if you use a smaller delta t, you get better accuracy. But don't forget, if you use a small delta t, that means you have to do more steps, right? If you calculate a time interval of 1 second and use a time step of 0.1 second, then you have to do 10 calculation, because 1 divided by 0.1 is 10. But if you do it with a smaller time step, if the time step is now 0.01, then you have to do 100 calculation, right? If you do it with a time step of 0.001, then you have to do 1,000 calculation. Okay, although you can get a better accuracy by reducing the delta t, the trade-off is that you have to do more calculation, and you need more computational time and resource. Now, for the simplest problem you encounter in this course, it doesn't matter. Okay, you can use a very small delta t. An Excel spreadsheet can handle very easily. Okay, and yeah, Excel spreadsheet can handle a lot of data, hundreds of thousands of data without difficulty, and so that's not a problem. But when you go to senior year, and when you find a very difficult differential equation, then the things will not be so simple, and you have to do it. You have to balance this trade-off. You probably don't want to do a lot of calculation, and that may be very time consuming for even with a good computer. Now, but I emphasize that we use the simplest numerical scheme here. This I refer to the simplest numerical scheme. And there are some numerical schemes that will improve the accuracy of calculation very substantially, but without decreasing the delta t. And you will learn it in senior year. Okay. And I encourage you to try in your homework, you try to decrease your delta t and to see after you decrease the delta t, is the solution improved? Accuracy of the solution will it improve? Now let's work on the motion. Suppose we have this equation. This is the equation of simple harmonic oscillation, right? We encountered before. The acceleration is minus omega squared multiplied by the displacement. Now we solve it with the numerical method. And on the graph on the left, we use delta t equal to 0.01, and we get this solution. Now, of course, you know that the result. The result should be an oscillation. And by conservation of energy, the amplitude of the oscillation should not increase, right? It should remain constant. After the object oscillates back to this original position, it should go back to this original position and not overshoot than that position. Okay, but when you do it numerically, you will find that the result is different. You will find that the result actually, after one cycle of oscillation, the object actually overshoots the initial position a little bit. And these are the numerical error. This is not real. It comes from the fact that you have introduced a little bit amount of error by assuming this equation, which is not exact. Okay. So how do I know that this is error, but not the real thing? Well, I try to reduce it. I'll try to reduce the delta t. Instead of using 0.01, I now use 0.005, which is half of this. And I realized that after reducing the delta t, I find that the error is reduced. When I use a still small delta t, I find the error is further reduced. So these are the error, not the real thing, not the features of the original physics problem. So I know how to distinguish the error from the real physical result. And I know how to tolerate, because the error is always there. So I should learn how to tolerate those errors. Okay, so that is the idea. So how should I choose the delta t? How small should I choose the delta t? Now, we rely on these two approximations. And in doing this approximation, we assume the acceleration and the velocity to be almost constant in that small time interval delta t. But that is not true. That's only an approximation. Well, but how good is that approximation? Well, we know that every system has a certain time scale of variation. Like, for example, the velocity decay exponential with time. We have the tau as a time scale, right? When the time t is equal to tau, the velocity has decayed to only 37% of its initial value, right? So that is a time for the velocity to change substantially. So in order for time interval delta t such that the velocity doesn't change much, you have to choose the delta t to be at least much smaller than this time scale tau. Now, for this time scale tau, you have a substantial change. And if you choose a delta t to be much smaller than tau, the change is negligible. And that is a suitable delta t. So you should at least choose a delta t that is much smaller than tau. Okay. And for other motions, like, for example, oscillation, the typical time scale may be the period of oscillation. And the period is given by 2 pi over omega, right? So you should choose the delta t to be much smaller than the period in order to make the calculation accurate. That is how you choose the delta t. Okay. So a long lecture today, we stop here.